Okay, hello everyone and welcome to the National Maritime Museum and to our Ice Worlds Festival in partnership with the British Antarctic Survey. My name's Dr. Greg Brown. I'm going to be your host for today's talk. Just a quick message at the very beginning that if over the course of the last few days you unfortunately haven't been able to get onto one of our ticketed events for today, please do take a look at the front of your blue programs. There's a QR code and some additional tickets have been opened up on some of those programs, so if you would like to join them, please do look at those and see if you can join them now. We are having all sorts of different talks over the course of today, fantastic talks from various different scientists involved with the British Antarctic Survey. And your talk now is going to be from Rob Larter. He's the current Deputy Science Leader of Paleoenvironments at the British Antarctic Survey, and he's been working as a marine geophysicist with the survey since 1987. His research focuses on the history of ice sheets and glaciers in Antarctica and the Southern Ocean. So please, can we welcome Rob Larter.
So good afternoon, everyone. Thank you for coming along. I hope you're all enjoying Ice Worlds. So you've been introduced to me. I've been helped with the slides for this presentation by Martin Furlong and Matthew Palmer at the National Oceanography, who are an engineer and a physical oceanographer who've been involved in the development of Boaty McBoatface. Now, I've been asked to make this talk suitable for 14-year-olds. This is a little bit of a challenge for me because my usual audience is other scientists. So I'm going to do my best, but cut me a little slack, please. And I can see there are a few members of the audience who might not quite be 14. So my aim here today is to explain to you what is Boaty McBoatface and why is it going to the Thwaites Glacier. So some of you may know a bit about the history of the name Boaty McBoatface. So let's put that to one side. Boaty McBoatface is now a rash that scientists can program and send off on missions to collect data that would traditionally only have been collected by research ships. Now, before I go into more about Boaty, I want to explain to you about where Thwaites Glacier is and why there is so much interest in it. So, question for the younger members of the audience. Thwaites Glacier is in Antarctica. Which way do I need to go here? This is a Google Earth view looking down on the UK. You think up? Anybody else? Everybody says up. Let's see. The Earth is round. No, we're going down. Going down the Atlantic Ocean, past Africa, past South America, and then if we keep going down, we get to a great white continent. So this is where Thwaites Glacier is. The blue area there. And it's the other thing I want to... So why is there so much... It looks quite small relative to Antarctica. Why is there so much interest in it? Well, in simple terms, the reason is the implications it might have for future sea level. But the one other thing I want to mention to you while we're here is it's incredibly remote. The nearest permanently occupied locations are the research stations operated by the British Antarctic Survey at Rothera on the Antarctic Peninsula and by the US Antarctic Programme at McMurdo in the Ross Sea. And both of those are about 2,000 kilometres away. So putting people here takes a number of aircraft flights, or if you're going by ship, it takes a whole week to get there from South America. So how much, another question for the young people, of all the ice in the world, what proportion of it do you think is in Antarctica? 19. Sounds a bit the same. Actually, 90% of all the ice in the world is in Antarctica. And if it was all instantaneously melted and put into the oceans, that would cause global sea level to rise by 58 meters. Don't panic. That's not going to happen in the lifetime of anybody here. It's not going to happen in the lifetime of the great-great-great-grandchildren of anybody here. But it's a lot of ice. And we only, if even a small proportion of it ends up in the ocean, that can result in a sea level rise, which is going to cause major problems worldwide. So the map I've got here, based on satellite data, is showing us how the Antarctic ice sheet has been changing since the early years of this century. So the blue areas have been gaining a little bit of ice. The surface of the ice is getting a little bit higher. The orange areas are losing ice, and the red and even the purple areas are losing a lot of ice. So there's the outline of Thwaites Glacier in that light blue area. You can see that this is in the center of an area that's losing quite a lot of ice. And I said about it appearing to be small relative to Antarctica. It is actually huge. This isn't like a glacier you might go and look at in the Alps. This is a glacier the size of a country like the UK at the same scale. Really, the area is about the same as the main island of Great Britain. So, one more thing I want to say about Antarctica here. We talk about the Antarctic ice sheet, but often scientists, we regard it as two ice sheets. The East Antarctic ice sheet, outlined in orange here, EAIS, and that is mostly sitting on rock above sea level. We're less concerned about that. The area that is the real source of concern for future sea level rise is the West Antarctic ice sheet, WAIS, outlined in red there. And you can see that most of the West Antarctic ice sheet has been losing ice over recent years. So this is the area we're concerned about. So why are we concerned about the West Antarctic ice sheet? Well, the reason is essentially that most of it sits on a bed that is below sea level. And some parts of that bed go very deep. As you go up glacier, back up flow, it gets deeper and deeper to more than 2 kilometers below sea level in the interior. And particularly the Thwaites Glacier drainage basin, virtually all of that is below sea level. So the blue cut, this is the bed. This is a map of the bed of the Antarctic ice sheet, the depths of the bed. All the blue areas are below sea level. The yellow and red, orange are above sea level. And the deep blue is a long way below sea level. So a long time ago, decades ago, glaciologists thought about this sort of configuration of a glacier. And they realized there's a potential instability there that if a retreat starts on a glacier whose bed gets deeper upstream, this could start to run away. It could be a runaway retreat. And now the reason for this, I've got a slide that I can explain this on here. Don't be scared. This is the most complicated slide, so pay attention, but don't be scared. It's got scary mathematical symbols on it. We won't go into any mathematics. Don't worry about that. So if a glacier is on a bed below sea level, at some point, the downstream end is going to go afloat, and we call that bit an ice shelf. And that is, of course, floating. So by Archimedes' principle, it's already displacing its own weight in water. We can consider that already lost to the ice sheet. So it's already part of the ocean. So the gateway between the ice in the ice sheet and the ocean is this point where it goes afloat, the grounding line. And what you can see here is if that grounding line, for any reason, retreats a little bit, the ice passing through it, the gateway has become wider. So even if it's flowing at the same rate, you're transferring more ice from the ice sheet to the ocean. Another thing you're doing, which I'll come to later, is you're exposing a greater thickness of the ice to the water. And if the water's warm, that becomes a real problem. So that's come to Thwaites Glacier. This is the front of Thwaites Glacier in a satellite image. And it's just like that conceptual section I showed you. The end of it ends up as floating ice, these ice shelf areas. There are two areas, one which we call the eastern ice shelf, one which we call the glacier tongue. And that's a satellite image from 2 years ago. And coincidentally, just a couple of days before that satellite image was collected, I took this photo from a research ship right at the front. That's what it looks like, kind of on the ground or on the sea if you're on a research ship. We weren't playing, actually. This wasn't a tourist trip. We were collecting data as we went along the front of this. What we were doing was mapping the ocean floor, seeing how deep it was there. So ice shelves are actually an incredibly important part of the ice sheet, but they're incredibly fragile as well. Over the past 30 years, there have been a number of instances where ice shelves, it's fair to say what's happened to them, they've collapsed. The best recorded one of these, the best documented, is the collapse of the Larsen B ice shelf, which was on the east side of the Antarctic Peninsula, which just completely collapsed in just a couple of months in early 2002. So this is a satellite image showing what the ice shelf looked like at the end of January 2002. And what I'll show you now is a GIF that cycles through a set of satellite images collected over the next 2 months. It'll go back. That's the beginning, and that's how it finished up. And it's just like the ice shelf just totally exploded in a couple of months. And while this may seem quite alarming, the really significant thing that was discovered when this happened is from looking at what happened to the glaciers that had been feeding into that ice shelf after it collapsed. Over the next year, the flow rates on those glaciers increased quite significantly. So they were putting more ice into the ocean, making a bigger contribution to sea level change. So this shows us beyond any doubt that ice shelves have an important role in holding back glaciers, in restricting their rate of flow. So what about Thwaites Glacier ice shelves? Well, you know where Thwaites Glacier is now. All the ice shelves shown in yellow here are pretty fine at the moment. The ones in orange and red are thinning. They're losing a lot of ice. And you can see all the ice shelves in the region around Thwaites Glacier are thinning quite rapidly. And we know the reason for that. It's not surface melting. This is an important point to understand. Even today, the temperatures don't get warm enough where Thwaites Glacier is for significant surface melting to happen. What's happening is it's warm water that's originating from the deep ocean that's coming against the front of the glacier that's causing the melting. And this map shows you the temperatures of the water at the seabed all around Antarctica. Where there's a blue shading, the water at the seabed is quite cold. It's not really going to cause much melting. Where there's a pink shading, that's where you've got relatively warm water at the seabed. So if we look at this in a section, along that purple line, this is a section through the ocean approaching Thwaites Glacier. Well, in fact, it's approaching the neighbour of Thwaites Glacier, Pine Island Glacier. So it goes from the deep ocean on the left to Pine Island Glacier on the right. The black is the shape of the seafloor. The blue colours are the cold surface water, and the red and orange colours are the relatively warm water coming from the deep ocean. Now, you'd normally expect warm water to sit on top of cold water, but the warm water here, this water out here is saltier, which makes it denser. So the warm water actually is mostly below about 400 meters water depth. So where it comes into contact with the ice, it goes into the cavities underneath the floating bit of the ice, and it melts these ice shelves from below, not from right from the front, but from below. So this is everything that's happening there is quite hidden. And by the way, we're not talking about warm water that you'd want to take a bath in here. These are the temperatures relative to the in situ freezing melting point of ice. So about 3 degrees above the temperature that you would freeze at. So you wouldn't want to even dip your toes in it, really. But that's a lot of heat energy for melting ice. So what's going on the Thwaites ice shelf over just the last few years? Well, this is really hot off the press satellite data. So because the ice shelf is floating, if you look with a satellite at how the surface elevation of that ice shelf is changing, you can work out what the thickness of the ice is. So on the left, we have a map that's showing us how the surface of the ice shelf is changing, and everywhere that's pink and red has been going down just over the last 3 years. And from that, you can calculate how much it's thinning, how much it's melting at the base. And so again, over here, everything that's pink and red, it's melting a lot at the base. The dark red, it's losing 20 meters of ice every year. So, probably these ice shelves are not going to last very long. I've seen scientists making projections of this. These ice shelves are probably going to disappear in a decade, maybe a bit longer if we're lucky. And then we'll see what happens to Thwaites Glacier. So, but the important point here is that what's going on is in this hidden world under these ice shelves. We need to find out where and how warm water is accessing these spaces, where it's going when it gets under there, where it makes contact with the base of the ice, if we're going to really accurately predict what's going to happen in the future. So this is where Boaty McBoatface comes in. So, but before I show you some pictures, tell you more about Boaty McBoatface, just some pictures of the general environment. This is the research ship that went, the American research icebreaker, Nathaniel B. Palmer. I went there in 2019 and 2020. That's not actually the ice shelf. That's big tabular icebergs in the background that have broken off the ice shelf. This is from the British Antarctic Survey's geophysical survey aircraft, a Twin Otter, that flew detailed airborne geophysical surveys over the front of Thwaites Glacier a few years ago, and that's a photo taken out the window looking southwards towards the ice shelf. That's what it looks like. More specifically, this is the kind of environment that Boaty will be deployed in, just at the front of the ice shelf. These are a couple of photos I took 2 years ago, right along the front of the ice shelf. And very conveniently, a seal agreed to sit there for me on an ice floes for scale. That's a seal. So that's an idea of this kind of scale that you're looking at. But also remember that 9/10 of floating ice is below water. So when Boaty is deployed in this environment, before it can go into this cavity, it's going to have to dive down 300 or 400 meters. So coming to Boaty McBoatface, that's what it looks like. It's a kind of yellow torpedo-shaped object, about 3 meters long. And this is what the boaties look like when you take the lid off them. And I'm giving the game away here. There's not just one boaty, there's a family of them. There's at least 6, because there are 3 of the type at the back there and 3 of the type at the front. And these are the 2 main types. One is designed for maximum endurance. It can go out and do missions up to 6,000 kilometers long before it comes back and wants to be picked up. Another type is designed for being able to dive really deep, 6,000 meters. What you're seeing here mainly is the pressure vessels inside, and the pressure vessels actually have all the important bits in, all the electronics and all the batteries. And the point there is that anything that you're putting to submerge in the ocean, you need to protect delicate electronics from the seawater, and you need to prevent it from being crushed by the immense pressures it's going to be subjected to. Now, the boaties don't just carry one fixed set of scientific instruments. They're flexible platforms that you could put a range of instruments on, but generally they will have sensors that will record the basic parameters about the ocean. They will record the temperature and the salinity and the dissolved oxygen content, but you can put things like cameras and sonar systems on these as well. And that brings us to boaties. If you're going to send a boaty under an ice shelf, you've got a particular issue. That boaty needs to be able to make sure it doesn't crash into things. And the bottom of an ice shelf is much rougher than the top. And also, generally, we know very little about the shape of the seafloor under an ice shelf because we can't survey that very easily. So a boaty that's going to go under an ice shelf needs to be smart. It needs to be able to sense its environment. So a lot of effort has gone into developing something called an obstacle avoidance system, OAS here. So these images show you the stages in development of an obstacle avoidance system. So what the smart engineers at National Oceanography Centre have done is they've taken a sonar system that sends out pulses of sounds and listens to the echoes, put that on the front of the autosub long range of the boaty, so it's sending pulses of sound forwards and listening for echoes, like a dolphin navigates underwater, or like a bat navigates in the dark, in the air. So these are the stages. I mean, when you're designing any complex engineering system, you start with a computer-aided design model, and then you try and build it, and then you put it in an experimental tank to test it, and then when you think it's ready, you take it to a bit of the natural environment. And earlier this year, they took this boaty to Loch Ness, which is the second deepest loch in Scotland, to see how it would perform. And then in the bottom right here, we've got a sort of visualization of what that's going to look like when boaty is operating under the ice shelf. So that's where we are. And I mean, is it going to work? Well, we're going to find out very shortly, because right now the Boaty that's been modified in this way is on its way to a port in South America to go on another cruise on the Nathaniel B. Palmer this season. And January and February, the expedition's going to be at Thwaites Glacier, and they're going to try and send one of these boaties under the Thwaites Glacier, and hopefully it's going to come back with a lot of important information that we can use to work out what's going to happen there and how much that glacier is going to contribute to sea level rise in the future. So that's what I have at the moment. These are the points that I hope you've taken away from what I've said, that future change in the West Antarctic ice sheet is the largest uncertainty in projecting future sea level rise this century. Thwaites Glacier is the most vulnerable and the most rapidly retreating glacier in Antarctica, and there's good reasons to expect that retreat to accelerate. And if Thwaites Glacier retreats, that will increase the vulnerability of neighbouring glaciers. Ice shelves, which are floating extensions of glaciers over the sea, they act as a brake on glacier flow, but they're incredibly fragile. And the reason Thwaites Glacier is losing ice is warm water that's impinging on it from the deep ocean. So we've got Boaty McBoatface now, or Autosub Long Range, as the engineers who built it tend to refer to it as. It's been adapted to go under the ice shelves and find out exactly what's going on in those hidden worlds. And we're going to find out how well that goes over the next few months. I expect this expedition will make the news. You will, if you're searching for it on Google, you'll find stuff out about it. So thank you very much. I'm happy to take any questions.
Okay, a fascinating talk there. Do we have any questions from the audience? Yes, right to the front here.
On the boats themselves, where do the sensors sit? If the scientific equipment is like in the pressure vessel, how do you get the information?
So the question was in Boaty McBoatface. So where do the sensors sit inside the?
Well, different sensors will sit in different places. I think your question is, how do you get the information back? Yes. So the information is almost all recorded internally. You have to recover the submersible, and then you download the data. So yeah, there's a jeopardy in very long missions. You could collect a lot of data, and if you don't get the instrument, if you don't get the submersible back, you've not only lost a lot of money, you haven't got the data.
Yeah, question right to the front.
How fragile are the glaciers?
How far down are the glaciers?
How far down? How fragile?
Fragile, I do apologise.
Well, I mean, the illustration is that ice shelf. There's been a number of those kind of ice shelf collapses over the last 30 years. The Larsen B one is kind of the poster child, because we have great satellite images of it. And you can see that a whole ice shelf that was tens of kilometres across just fragmented in the space of a couple of months. And that's happened several times. So the glaciers themselves are a bit more robust. But over the last 10 years, apart from the marine instability hypothesis I tried to explain, there's also something called the marine ice cliff instability that people have highlighted, that if you take away an ice shelf and leave a cliff that's very tall, the weight of the ice itself could exceed the strength of the ice. And then you could start getting an even faster sort of retreat. I mean, this is the sort of principle when people are building tall buildings. They have to know the strength of the material, because if you build a tall building too tall, the concrete's going to start to fail.
Yes, right to the front.
Yes, I've got two questions. So the first question is there anyone, a human, steering and controlling this boat?
No, it's totally. The submersible, the boaties are totally autonomous, and their predecessors. So it's entirely. A mission is programmed, and obviously with the obstacle avoidance system, it needs to have some level of artificial intelligence. So if it meets an obstacle, it has to work out how to avoid it while deviating as little as possible from its mission.
And the second question is, what's powering this boat? Is it, what kind of fuel does it have? Is it electric?
It's all battery power. And at the moment, I'm afraid, okay, I'll come clean here. or come dirty, they are disposable batteries that are used at the moment because quite simply disposable batteries pack more energy density. The people, the engineers at NSC are experimenting with various rechargeable battery solutions at the moment, and they hope to implement those in the not too distant future.
Yes, at the back there.
I was wondering if you know the source of that warm water and why it's focused on that part of the western.
So the question is, what is the source of that warm water and why is it focused on the point that it is?
That's a very good question, and that's what a lot of research is geared to finding the answer to. We think there is a hypothesis, and we think this is true. We couldn't like put our hand on our heart, and say this is 100%. We're 100% sure of this, but it seems to be during the 20th century, probably related to warming of the ocean, the Pacific Ocean. There have been changes in wind patterns, and most of the Southern Ocean circulation is actually wind-driven. Most of the water in the Southern Ocean travels eastwards continuously around Antarctica, driven by winds coming from the west. We think because we don't have instrumental records that go back that far, this is one of the things that I'm engaged in. We're looking at natural archives to check this, sediment cores, ice cores. We think the wind patterns along the Antarctic continental margin in this part of Antarctica changed in the middle of the 20th century, resulting in warm water being driven onto the shelf.
Yes, yeah.
Has anyone thought about ideas to try and stop? Obviously, it'd be great if the cooler water was somehow lower down. Is it possible to, like, I don't know, spray salt across the border of the sea to try and get the temperature of the...
I mean, these are kind of geoengineering solutions. Yeah, there are a lot of sort of ideas out there. In general, when you start to examine them in detail, the efforts, the resources that would be involved in implementing any, even if it worked, would be immense. I mean, the remoteness of this area is the problem. You know, it's anything big you want to get in there, you're going to have to transport by ship. It takes a week by ship. The carbon emissions of going there on a ship and back, 2 weeks transit on a ship, and a lot of ships, are enormous. And then most geoengineering solutions, the problem is, the Earth's climate system is complex, and when you poke a complex system, you often get unexpected, there are unexpected things that can happen. So any kind of geoengineering solution, you need to be very sure you've really checked it out. So we could trigger things that we really don't want to. The best solution is like, let's stop changing the climate.
Yeah, right at the very front. How do you make sure they're waterproof?
Well, in the development of the boaties, they will have done lots of tests in experimental water tanks, big swimming pools effectively, and they'll monitor that to see if any water is getting in. I mean, if water does get in, you'll know quite soon because the electronics will start failing, and particularly with lithium batteries, that's not good. Yeah, I mean, it's trial and error, really. You'll have checked this out in experimental tanks before you put these things into the natural environment.
And we'll have one last question here.
Is anything to do with the El Nino current?
So is
El Nino current, the warm water that goes around?
Yeah, that's a field of scientific interest, is how are things that happen near Antarctica correlated with the El Nino, La Nina cycle. There is a degree of correlation, and indeed the amount of warm water that's coming onto the Antarctic shelf does seem to be, it correlates with the intensity of the El Ninos, or a lot of people think it does. And indeed, it's been suggested there were some very strong El Ninos in the 1940s, and we think that may have been when the first strong pulses of warm water started coming onto the Antarctic shelf. There's some evidence that some of my colleagues have found for that from sediment cores on the seafloor. We can see that some things changed dramatically around about the 1940s.
Okay, if we can thank then Rob Latta one more time. Thank you very much. And do have a look at the rest of the attractions and activities happening over the course of the rest of today. There will be more talks throughout the rest of the day. And don't forget to look up on the great map for all of the exhibits that are up there. We hope you enjoy the rest of your day.
Thank you.